We've put humans on the moon, landed rovers on Mars, sent probes beyond our solar system. So visiting the nearest star should be next, right? Dead wrong. Alpha Centauri is only 4 light-years away, and we have zero capability of getting there. Today we're going to explore what it would really take to visit our nearest stellar neighbor. And here is a question. If time travel becomes possible, which event in the past would you like to change? Let me know in the comments. I will pin the most creative answer. Now let's begin. The reality is far more complicated and more terrifying than most people realize. Proxima Centauri is an active red dwarf, meaning it regularly unleashes powerful stellar flares that bathe its planets in intense radiation. Recent research from NASA published in 2017 cast serious doubt on whether Proxima B could actually support life. These stellar eruptions threaten any potential atmosphere with oxygen loss, stripping away the very elements that might make a world habitable. X-ray observations from the XMM Newton telescope in 2026 revealed that Proxima's radiation environment is extraordinarily variable, with soft X-ray and extreme ultraviolet emissions that fluctuate dramatically over short timescales. Any life trying to gain a foothold on Proxima B would face a relentless bombardment that makes Earth's radiation environment look like a gentle spa treatment. But let's set aside the question of whether we should go to Alpha Centauri and focus on something even more fundamental. Could we actually make the journey? The challenges aren't just technical, they're existential. They force us to confront the absolute limits of what's physically possible in our universe. Let's start with propulsion. Every rocket ever built operates on a simple principle discovered by Isaac Newton. For every action, there's an equal and opposite reaction. You throw mass out the back of your spacecraft at high speed, and your spacecraft moves forward. The problem is that you need fuel to throw out, and that fuel has mass, which means you need more fuel to accelerate that fuel, which has even more mass, which means you need even more fuel to accelerate that fuel. It's a vicious cycle that mathematicians call the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, tells us that the final velocity of a spacecraft depends on the exhaust velocity of your engine and the ratio between your initial mass, with all that fuel, and your final mass, when the fuel is gone. To reach even a modest fraction of light speed using conventional chemical rockets would require a fuel-to-payload mass ratio so absurdly large that the numbers become meaningless. We're talking about needing more fuel than exists in the entire solar system just to accelerate a tiny probe to a few % of light speed. Chemical rockets simply cannot take us to the stars. They're magnificent for exploring our solar system, but for interstellar travel, they're about as useful as a bicycle for crossing an ocean. So scientists and engineers have proposed more exotic propulsion systems. Nuclear pulse propulsion, first conceptualized in the 1950s under Project Orion, would involve detonating nuclear bombs behind your spacecraft and riding the shockwave. It sounds insane, and in many ways it is, but the physics actually works. You could theoretically reach a few % of light speed this way. The problems are political, environmental, and practical. Launching a spacecraft laden with nuclear weapons from Earth's surface would be monumentous. If you're finding this journey through the cosmos as fascinating as I am, please hit that subscribe button and give this video a thumbs up. It helps this channel grow and allows me to keep bringing you these deep dives into the universe's greatest mysteries. But what about fusion rockets? Nuclear fusion, the same process that powers the sun, releases far more energy per unit of fuel than any chemical reaction. A fusion rocket could theoretically achieve exhaust velocities high enough to make interstellar travel feasible within human timescales. The catch is that we haven't yet built a fusion reactor that produces more energy than it consumes, let alone miniaturized one enough to fit on a spacecraft. Researchers have been working on controlled fusion for more than 70 years, and we're still not there. Projects like ITER in France are making progress, but we're still likely decades away from practical fusion power and even farther from fusion propulsion. Then there's antimatter. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy according to Einstein's famous equation E equals mc squared. No other energy source even comes close to this efficiency. The problem is that antimatter doesn't exist naturally in our region of the universe. We have to make it, atom by atom, in particle accelerators, and the process is staggeringly inefficient and expensive. Producing just 1 gram of antimatter would cost approximately $62.5 trillion at current production rates and consume more energy than the entire United States uses in a year. And that's just 1 gram. You'd need significantly more to fuel an interstellar journey. But perhaps the most intriguing proposal came in 2016, when physicist Stephen Hawking and billionaire Yuri Milner announced Breakthrough Starshot, an ambitious project to send tiny gram-scale probes to Alpha Centauri within a generation. The concept was beautifully elegant. Instead of carrying fuel, the spacecraft would be propelled by light itself. Enormous ground-based laser arrays would focus their beams on ultra-lightweight reflective sails attached to miniaturized probes no bigger than a microchip. Accelerated continuously by photon pressure, these nano-spacecraft could theoretically reach 20% of light speed, allowing them to reach Alpha Centauri in just 20 years. The vision captivated the world. Here, finally, was an approach that didn't violate the laws of physics or require impossible amounts of antimatter or centuries-long journeys. The plan called for developing laser systems capable of generating 100 gigawatts of power, sails just atoms thick but kilometers across, and spacecraft smaller than a postage stamp but packed with cameras, sensors, and communication equipment. Upon arrival, these tiny emissaries would photograph the Alpha Centauri system, study its planets, and beam data back to Earth using their own tiny lasers, a transmission that would take another 4.37 years to reach us. But here's where the story takes a sobering turn. In September 2025, Scientific American magazine revealed what those of us following the project had begun to suspect. Breakthrough Starshot had quietly failed. According to the report, Milner never came close to providing the promised $100 million. Estimates suggest that at most $4.5 million was actually distributed. The project consisted mainly of meetings between different research groups, each working on isolated aspects of the challenge. Some teams never received any funding at all. Others got a few tens of thousands or at most a few $100,000, enough to keep preliminary research alive, but nowhere near enough to solve the fundamental engineering problems. And those problems are truly daunting. A spacecraft traveling at 20% of light speed would collide with interstellar hydrogen atoms and dust grains with relativistic energy. In the spacecraft's reference frame, these stationary particles would appear as a nearly monoenergetic beam of charged particles slamming into the leading edge. Each collision would produce radiation, Bremsstrahlung photons, secondary particles, and nuclear reactions. A study published in the Astrophysical Journal in 2022 calculated the radiation doses such a spacecraft would receive. The numbers were sobering. Electronic components would be destroyed. Even shielding thick enough to protect sensitive equipment would add so much mass that the whole concept breaks down. Then there's the communication problem. To send data back to Earth from 4.37 light-years away using a tiny laser mounted on a gram-scale spacecraft, you'd need absurdly precise pointing accuracy. The beam would have to stay locked on Earth despite the craft's tumbling motion, despite having no significant attitude control thrusters, despite the Doppler shift from traveling at relativistic speeds. The engineering challenges multiply like rabbits, each one spawning several more. The failure of Breakthrough Starshot teaches us something profound about the gap between conceptual elegance and engineering reality. The physics might allow for light sail propulsion, but the technology required is so far beyond our current capabilities that even billionaire funding couldn't bridge the chasm. This is the harsh truth about interstellar travel. The universe doesn't care about our ambitions. The laws of physics are indifferent to human timelines and budgets. But let's imagine for a moment that we solve the propulsion problem. Let's say we develop a spacecraft capable of reaching 10% of light speed, a conservative estimate compared to Breakthrough Starshot's goals, but still monumentally faster than anything we've ever built. Even at this incredible velocity, the journey to Alpha Centauri would take approximately 43 years. That's nearly half a human lifetime. But the challenges don't end with propulsion. In fact, they're only beginning. Consider what happens when you're moving at a significant fraction of light speed through interstellar space. Space isn't actually empty. It's filled with an incredibly diffuse gas of hydrogen atoms, averaging about 1 atom per cubic centimeter in the interstellar medium near our solar system. At normal spacecraft velocities, these atoms are completely harmless, but at 10% of light speed, each hydrogen atom becomes a microscopic bullet carrying tremendous kinetic energy. The faster you go, the worse it gets. Physicists have calculated that at 20% of light speed, collisions with interstellar hydrogen would produce radiation doses equivalent to being inside a nuclear reactor. The spacecraft would need shielding several meters thick to protect any electronics or, heaven forbid, any crew. But remember the rocket equation: every kilogram of shielding is mass you have to accelerate, which requires more energy, which requires more fuel, or larger lasers, which makes the entire enterprise even more difficult. There's no easy solution. You're caught between radiation death and mass penalties that make the journey impossible. And here's something that will really bend your mind. Time itself becomes strange when you travel at relativistic speeds. Einstein's theory of special relativity tells us that time passes differently for objects moving at different velocities. It's not an illusion or a trick. It's a fundamental feature of how the universe works. If you're on a spacecraft traveling at 90% of light speed, time for you would pass at roughly 44% the rate it passes for someone on Earth. A journey that takes 10 years by your onboard clock would consume nearly 23 years of Earth time. This phenomenon, called time dilation, gets more extreme as you approach light speed. At 99% of light speed, the difference becomes dramatic. 1 year for you equals roughly 7 years for Earth. At 99.9%, 1 year for you equals 22 years for Earth. This creates a profoundly isolating situation. Astronauts traveling to Alpha Centauri at high relativistic speeds would return to an Earth that had aged decades or even centuries more than they had. Everyone they knew would be elderly or dead. Society would have transformed. They would become temporal refugees, strangers in their own future. But here's the really terrifying part. You can't just flip a switch and instantly travel at 90% of light speed. You have to accelerate, and that acceleration has to be gentle enough that it doesn't turn your crew into biological pancakes. The human body can withstand about 4 to 5 times Earth's gravity for extended periods before serious health problems develop. Fighter pilots experience brief moments of much higher G-forces, but sustaining even 3 or 4 Gs for days or weeks would be brutally punishing and potentially fatal. Let's do some math. If you accelerate constantly at 1 G, exactly Earth's surface gravity, which would feel perfectly comfortable for the crew, you could reach 10% of light speed in approximately 35 days. That's actually not too bad, but here's the catch. You need to decelerate at the other end, or you'll shoot past Alpha Centauri at 30,000 kilometers per second with no way to stop. So you accelerate for half the journey, then flip your spacecraft around and decelerate for the second half. This maneuver doubles your travel time and doubles your fuel requirements. Speaking of fuel requirements, let's talk about just how much energy we're discussing here. The kinetic energy of an object is 1/2 its mass times its velocity squared. When velocities approach the speed of light, you need to use the relativistic formula, but the basic principle holds. Energy requirements increase dramatically with speed. To accelerate just 1 kilogram to 10% of light speed requires approximately 450 trillion joules of energy. That's equivalent to about 108 tons of TNT for a single kilogram. A modest interstellar spacecraft with crew, life support, radiation shielding, and scientific equipment might mass 100 metric tons. To accelerate that to 10% of light speed would require energy equivalent to 4.5 million tons of TNT, or roughly 300 Hiroshima bombs. And that's just to accelerate. You need the same amount again to decelerate. And we haven't even accounted for the mass of the fuel itself, which makes the rocket equation rear its ugly head once more. By the way, if you found the discussion about distances terrifying, you might want to check out my video called The Terrifying Distance to Andromeda, where we explore what it means to contemplate traveling not just 4 light years. The challenges we're discussing for Alpha Centauri multiply into nightmare scenarios when we consider intergalactic distances. The link is in the description and on the card above. Now let's address another challenge that science fiction rarely mentions: navigation and communication. At interstellar distances, you can't just point your spacecraft in the right direction and hope for the best. Stars move. Alpha Centauri has a proper motion, that is, motion across our line of sight, of about 3.85 arc-seconds per year. Over the decades-long journey, the star system will have moved significantly from where it appeared to be when you launched. You need to constantly update your trajectory, which requires precise knowledge of your position and velocity. But how do you know where you are in the vast emptiness between stars? On Earth, we use GPS satellites. In near-Earth space, we can use radio signals from ground stations, but halfway to Alpha Centauri, you're 2 light-years from the Sun and 2 light-years from your destination. There are no convenient landmarks, no reference points except the stars themselves. You'd need to use stellar parallax, measuring tiny shifts in star positions as you move, to triangulate your location. This requires extraordinarily precise measurements and complex calculations. A tiny navigation error could cause you to miss the Alpha Centauri system entirely, sailing past it into the infinite void beyond. Communication presents equally daunting problems. Radio signals travel at the speed of light, which means a transmission from Earth to a spacecraft near Alpha Centauri takes 4.37 years to arrive. Ask a question from Mission Control, and you'll wait nearly 9 years for a response. This isn't just inconvenient, it makes real-time mission management impossible. The crew would be entirely on their own, making decisions without input from Earth, knowing that any crisis they face cannot be solved by calling home for help. And the signal itself degrades over distance according to the inverse square law. Double the distance and your signal spreads out over 4 times the area, becoming 1/4 as strong. At interstellar distances, even powerful transmitters become whispers. The radio dishes used to communicate with Voyager 1, currently the most distant human-made object at about 163 astronomical units from Earth, are enormous, 70 meters in diameter. And Voyager's signal, transmitted with just 23 watts of power, less than a household light bulb, is barely detectable even with these massive antennas. Alpha Centauri is roughly 16,000 times farther away than Voyager. The communication challenges are staggering. Then there's the psychological dimension, which might be the most terrifying aspect of all. Imagine being sealed inside a spacecraft the size of a small house with a handful of other people for 40, 50, or 60 years. You can never go outside, you can never feel wind on your face or rain on your skin, you can never walk on grass or swim in the ocean. Every breath of air you take has been recycled countless times through machines. Every drop of water you drink has been purified from waste products. The same walls surround you every single day, year after year, decade after decade. Studies of isolated environments like Antarctic research stations and submarines have shown that even highly trained, psychologically screened individuals can develop serious mental health issues after just months of isolation. Depression, anxiety, interpersonal conflicts, and cognitive decline are common. And those people know they can eventually go home. An interstellar crew would have no such comfort. For the first years of their journey, they could theoretically abort and return to Earth, though the social and financial costs would be enormous. But past a certain point, the halfway mark, they're committed. Turning back would take just as long as pushing forward. They're trapped in a metal can, hurtling through the void, and the only way out is through. The radiation environment inside the spacecraft would be another constant threat to both physical and mental health. We've talked about radiation from collisions with interstellar hydrogen, but there's also cosmic radiation, high-energy particles from exploding stars, active galactic nuclei, and other violent cosmic events. These particles carry so much energy that they can penetrate meters of shielding. When they pass through living tissue, they can damage DNA, increasing cancer risk and potentially causing cognitive impairment. Studies of astronauts who've spent time on the International Space Station, which is still protected by Earth's magnetic field and is only about 400 kilometers up, have shown measurable vision problems, likely caused by fluid shifts in microgravity, as well as bone density loss, muscle atrophy, and immune system changes. An interstellar crew would face all these same issues, but for decades instead of months, with no possibility of medical evacuation if something goes seriously wrong. They would essentially be conducting a decades-long medical experiment on themselves with no control group and no backup plan. Let's talk about life support, because keeping humans alive for decades in a sealed environment is far more complex than most people realize. On Earth, we take for granted the incredible ecological systems that sustain us. Plants absorb carbon dioxide and release oxygen through photosynthesis. Bacteria in soil break down waste and recycle nutrients. The water cycle purifies and redistributes moisture. Temperature is regulated by atmospheric circulation and ocean currents. We live inside a perfectly balanced biosphere that took billions of years to evolve, and we're planning to replicate it inside a spacecraft. The International Space Station provides a sobering reality check. It requires regular resupply missions from Earth carrying water, food, oxygen, spare parts, and other essentials. The life support systems are constantly breaking down and being repaired. Air filters clog, water recyclers malfunction, equipment fails in unexpected ways. And the ISS is only 400 kilometers from Earth, with resupply missions arriving every few months. An interstellar spacecraft would have no such luxury. Everything must work perfectly, or the crew dies. There are no spare parts stores in interstellar space, no repair technicians you can call, no rescue missions coming to save you. The spacecraft would need to be almost entirely self-sufficient, operating as a closed ecological system. Water would be recycled from every possible source, humidity in the air, urine, sweat, even the moisture in exhaled breath. Current ISS recycling systems recover about 93% of water, which sounds impressive until you realize that 7% loss rate compounds over time. On a 40-year mission, you'd need to carry substantial water reserves just to account for recycling inefficiency, and water is heavy. Each liter masses 1 kilogram. Oxygen presents similar challenges. Plants could theoretically generate oxygen through photosynthesis, but you'd need substantial growing area and powerful lights to support enough plant life to sustain a crew. Those lights require energy, which requires either massive solar panels, which add mass and become less effective as you move away from the sun, or nuclear reactors, which add mass, complexity, and radiation concerns. Alternatively, you could electrolyze water to produce oxygen, but that also requires significant energy and slowly depletes your water reserves unless you can perfectly recycle every molecule. Food is perhaps the most challenging aspect. Humans require roughly 2,000 calories per day, along with specific nutrients, vitamins, and minerals. On a 40-year mission with a crew of, let's say, 6 people, you'd need approximately 175 million calories total. If you tried to carry all that food as freeze-dried rations, you'd need roughly 43,000 kilograms of food, 43 metric tons. That's mass that must be accelerated to relativistic speeds and then decelerated at the destination. The energy costs are prohibitive. The alternative is to grow food aboard the spacecraft. But agriculture in microgravity presents enormous challenges. Plants need gravity to orient their roots and shoots. In zero gravity, roots grow in random directions, and plants struggle to transport nutrients effectively. You'd need to create artificial gravity through rotation, which introduces a whole new set of engineering complications. The spacecraft would need to be designed as a rotating structure, perhaps a cylinder or torus, spinning fast enough to create centrifugal force equivalent to Earth's gravity at its outer rim. But rotating structures create problems of their own. The Coriolis effect would make moving around feel strange and potentially nauseating. Drop something and it wouldn't fall straight down, it would curve as it fell. The engineering required to build a large rotating structure strong enough to withstand decades of continuous stress, yet light enough to accelerate to relativistic speeds, pushes the boundaries of materials science. You'd need materials stronger than anything we currently mass produce, perhaps carbon nanotubes or graphene composites that exist only in laboratories today. And we haven't even discussed what happens when things go wrong. On Earth, if your air conditioning breaks, you open a window. If your water heater fails, you call a plumber. If you get sick, you go to a hospital. On an interstellar spacecraft, the crew must be able to diagnose and repair any conceivable problem with zero outside help. They would need to be expert mechanics, electricians, computer programmers, medical professionals, and psychologists all rolled into one. The spacecraft would need to carry extensive spare parts, diagnostic equipment, and tools for every system. Medical emergencies are particularly terrifying to contemplate. What happens if someone develops appendicitis 15 years into the mission? On Earth, that's a routine surgery. In space, with no trained surgeon and limited medical facilities, it could be a death sentence. What about cancer caused by radiation exposure, cardiovascular disease, dental problems? The crew would need enough medical knowledge and equipment to handle everything from minor injuries to major surgeries, all while dealing with the complications that microgravity or artificial gravity introduced to healing and recovery. Then there's the question of governance and social structure. Who's in charge? How are decisions made? What happens when conflicts arise? And they will arise because you're talking about humans living in close quarters under extraordinary stress for decades. Do you vote democratically on major decisions? Does the mission commander have absolute authority? What if the commander becomes incapacitated or makes decisions the crew believes are dangerous? There are no police, no courts, no higher authority to appeal to. The crew must develop and maintain social cohesion entirely on their own, knowing that serious conflict could doom the entire mission. History provides some disturbing precedents. Antarctic expeditions, naval voyages, and isolated settlements have all experienced breakdowns in social order under far less stressful conditions and far shorter timescales. Mutinies, psychological breakdowns, violence, these aren't just theoretical concerns. They're documented patterns of human behavior in isolated environments. An interstellar crew would need extraordinary psychological resilience and conflict resolution skills. Screening and training could help, but there's no way to perfectly predict how humans will behave when subjected to decades of isolation and stress. Now let's address something truly mind-bending: relativistic effects on the universe itself. We've discussed time dilation, but there are other strange consequences of traveling at high speeds. One is called relativistic aberration, the apparent distortion of the positions of stars. As you approach light speed, stars directly ahead of you appear to shift forward in your field of view, while stars behind you seem to cluster toward the rear. The entire star field becomes distorted, with colors shifting due to the Doppler effect. Stars ahead of you would appear blue-shifted, their light compressed to higher frequencies, while stars behind would appear red-shifted. At very high speeds, the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, would become dangerously concentrated in the forward direction. This radiation, normally just a few degrees above absolute zero and completely harmless, would be blue-shifted into the X-ray and gamma-ray spectrum directly ahead of your spacecraft. You'd essentially be flying into an increasingly intense radiation beam created by your own motion through space. This is yet another source of radiation that would batter your spacecraft and threaten both electronics and crew. There's also the problem of interstellar dust. Space isn't uniformly empty. There are regions of higher and lower density, and occasionally you encounter dust grains. At normal spacecraft speeds, these tiny particles are harmless. At 10% of light speed, a grain of dust massing just 1 microgram carries kinetic energy equivalent to a hand grenade. At 20% of light speed, that same grain hits with the energy of several kilograms of TNT. Your spacecraft would need shielding strong enough to withstand these hypervelocity impacts, or, alternatively, some kind of forward sensor system and rapid response thrusters to dodge obstacles, which seems impossible given the speeds and distances involved. Some researchers have proposed a sacrificial shield, a thick slab of material mounted ahead of the spacecraft to absorb impacts, slowly eroding over the course of the journey. But this adds mass, and the shield itself creates secondary radiation when particles impact it. You're trading one problem for another, never quite eliminating the danger, only managing it to hopefully survivable levels. Let's zoom out for a moment and consider the cosmic perspective. Alpha Centauri is our nearest stellar neighbor, and the challenges of reaching it are almost overwhelming. But in the grand scheme of the galaxy, 4.37 light-years is practically nothing. Our Milky Way galaxy is roughly 100,000 light-years in diameter. The distances we've been discussing, which seem so impossibly vast, represent less than 1/20,000th of our galaxy's width. We're talking about crossing the cosmic equivalent of a single step, and already the obstacles seem nearly insurmountable. This should give us profound humility about our place in the universe. We are a young species only recently emerged from our home planet, taking our first tentative steps into space. The Voyager probes, launched in 1977, have only just begun to enter interstellar space after nearly 50 years of travel. At their current speeds, they would take over 70,000 years to reach Alpha Centauri if they were headed in that direction, which they're not. In cosmic terms, we're still infants, barely able to crawl, dreaming of running marathons. But here's the beautiful thing: recognizing these challenges doesn't mean giving up. It means understanding what we're up against and working methodically to solve each problem. Every generation of humans has faced challenges that seemed impossible with the technology and knowledge of their time. Crossing oceans, flying, splitting the atom, visiting the moon, all were once considered fantasy or impossible. The key is patience, persistence, and the willingness to think across generations rather than within individual lifetimes. Some scientists have proposed generation ships, enormous vessels that would take centuries to reach their destination, with multiple generations born, living, and dying aboard during the journey. The people who arrived at Alpha Centauri would be the great-great-great-grandchildren of those who launched. They would know Earth only through records and stories, having spent their entire lives in transit. The social, ethical, and psychological implications of such a mission are staggering. Would children born aboard have any choice about their destiny? How would you maintain cultural continuity across generations? How would you prevent technological knowledge from degrading over time? The concept of generation ships forces us to confront uncomfortable questions about autonomy and consent. The original crew would make a choice to embark on this journey, but their children wouldn't have that choice. They would be born into a mobile prison, unable to ever experience the planet their ancestors left behind, or to deviate from the course set by people who died before they were born. It's a kind of temporal tyranny, benevolent perhaps in intention, but tyrannical nonetheless in its absolute constraint of future generations' freedom. And what about the return journey? Would anyone attempt to come back? By the time the ship reached Alpha Centauri, several generations would have passed on Earth as well. The society that launched the mission would be ancient history. Political systems would have changed, languages would have evolved, technology would have advanced beyond recognition. The returning crew, or their descendants, would be strangers to a world that had moved on without them. It's quite possible that a generation ship, once launched, would never return. Its passengers would become permanent exiles, founding a new branch of humanity among other stars. Some futurists have proposed an alternative: suspended animation or cryogenic preservation. If you could place the crew in a state of suspended biological function, they wouldn't age during the journey. A 40-year voyage would pass in what felt like moments. They would go to sleep near Earth and wake up near Alpha Centauri, biologically the same age they were when they left. This would solve the psychological challenges of decades-long isolation and the practical challenges of life support. Frozen people don't need food, water, or oxygen. But here's the problem: we can't actually do this. Despite what science fiction suggests, cryogenic preservation of living humans remains firmly in the realm of speculation. We can freeze cells, embryos, even some small organisms, and successfully revive them. But whole humans, the challenges are immense. When water freezes, it expands, and ice crystals form. Those crystals puncture cell membranes, destroying tissue at the microscopic level. By the time your body reaches cryogenic temperatures, massive cellular damage has already occurred. Researchers have experimented with cryoprotectants, chemicals that prevent ice crystal formation, and have achieved some success with vitrification, a process that turns water into a glass-like solid rather than crystalline ice. But scaling this up to preserve an entire human body without damage remains far beyond our current capabilities. And even if we solved the freezing problem, we'd still need to solve the thawing problem. How do you warm a frozen body uniformly and rapidly enough to prevent damage while ensuring all cellular processes restart correctly? Nobody knows. There's also the matter of maintaining frozen bodies for decades. A single power failure, a malfunction in temperature regulation, and your crew thaws prematurely, or worse, partially thaws and refreezes, sustaining catastrophic tissue damage. The spacecraft would need redundant cooling systems with perfect reliability over timescales far exceeding anything we've engineered before. And unlike awake crew members who can notice problems and make repairs, frozen passengers are completely helpless, dependent entirely on automated systems that can't improvise or adapt to unexpected situations. Some scientists have proposed pharmacological hibernation as an alternative, using drugs to slow metabolism dramatically without actually freezing the body. Bears and other hibernating animals provide a biological proof of concept. During hibernation, a bear's heart rate drops from around 50 beats per minute to just 8 to 10. Body temperature decreases by several degrees. Metabolism slows dramatically, allowing the animal to survive months without food. If we could induce a similar state in humans, we might reduce life support requirements and slow aging without the dangers of freezing, but human hibernation remains theoretical. We don't fully understand the biochemical mechanisms that allow bears to hibernate without suffering muscle atrophy, bone loss, or blood clots. All problems that plague bedridden humans after just weeks of inactivity. Some research suggests that specific combinations of metabolic suppressants, temperature reduction, and perhaps genetic modification could induce a hibernation-like state in humans, but we're nowhere close to testing this on actual people, let alone relying on it for interstellar missions. Let's consider another radical approach. Don't send humans at all. Send artificial intelligence. A robotic probe wouldn't need life support, wouldn't go insane from isolation, wouldn't require food or water, and could potentially function for centuries with minimal maintenance. Modern electronics are far more radiation-resistant than biological tissue, though still vulnerable, and can be heavily shielded without the mass penalties associated with protecting fragile humans. A robotic mission to Alpha Centauri is technologically much more feasible than a crewed mission. But this raises philosophical questions. Is a mission without humans really a human achievement? What's the point of exploring if we don't experience it ourselves? Some would argue that sending our robotic emissaries is enough, that expanding human knowledge and presence through our creations counts as human exploration. Others feel that something essential is lost when flesh and blood humans aren't present to witness and experience the journey firsthand. There's no objectively correct answer. It depends on how we define the purpose of exploration. Robotic probes also face the communication delay problem we discussed earlier. A probe at Alpha Centauri can't be remotely piloted in real time. The nearly 9-year round-trip light delay makes that impossible. It would need sophisticated artificial intelligence capable of autonomous operation, scientific data collection, and problem-solving without human intervention. Given the current state of AI technology, this seems achievable within a few decades. The question is whether we can miniaturize such intelligence enough to fit on a spacecraft light to accelerate to relativistic speeds. Now let's talk about what we'd actually do upon arriving at Alpha Centauri. You can't just slam on the brakes. As we discussed, you need to decelerate, which requires just as much energy as acceleration. If you're using a rocket-based propulsion system, you need to carry fuel for deceleration, which makes your initial mass even larger, which requires more acceleration fuel, which compounds the mass problem into absurdity. If you're using a light sail pushed by lasers from Earth, you can't use the same method to slow down. The laser is 4 light-years behind you, and its beam has spread so much that it's useless. One proposed solution is a magnetic sail. As you approach Alpha Centauri, you deploy an enormous superconducting loop of wire, kilometers in diameter, that generates a powerful magnetic field. This field interacts with the charged particles of the stellar wind from Alpha Centauri's stars, creating drag that slowly decelerates your spacecraft. The physics is sound, but the engineering is daunting. You'd need to carry this massive structure folded up for decades, deploy it reliably at the end of your journey, and maintain superconducting temperatures in an environment bathed in radiation and stellar wind. Any failure means you scream past your destination into the void beyond. Another possibility is a 2-stage light sail. The first, larger sail accelerates the spacecraft. Partway through the journey, you separate from this sail and continue with a smaller one. The larger sail, now behind you, uses laser light still reaching it from Earth to reflect photons forward, effectively becoming a mirror that redirects laser energy to push against your smaller sail from behind, decelerating you. The geometry and timing need to be absolutely perfect, and the masses and sail sizes must be precisely calculated. One error and the whole elegant scheme falls apart, or you could simply accept that you're not stopping. A flyby mission screaming past Alpha Centauri at 10 or 20% of light speed would give you only hours or perhaps days to collect data as you whip through the system. High-resolution cameras, spectrometers, magnetometers, and other instruments would capture as much information as possible during that brief window, then spend years transmitting the data back to Earth. It's not ideal, but it's far simpler than trying to decelerate, and for an initial reconnaissance mission, it might be sufficient. But let's assume we solve the deceleration problem and successfully arrive at Alpha Centauri with the ability to explore the system. What would we find? Alpha Centauri A and B, as we've discussed, orbit each other in a complex dance. Planets in this system would need to orbit very close to one of the stars to maintain stable orbits, or very far from both, in wide circumbinary orbits. The habitable zone, the region where liquid water could exist on a planet's surface, would be a moving target, shifting as the two stars orbit each other with a period of about 80 years. Recent astrometric studies using the Hubble Space Telescope, published in February 2026, have refined our understanding of potential planets in the Alpha Centauri system. The research combined archival and recent Hubble observations with data from the Gaia Space Telescope to search for the subtle wobbles in stellar position that planets would cause. While no massive planets have been definitively confirmed orbiting Alpha Centauri A or B, the possibility of smaller, Earth-like worlds remains open. And then there's Proxima Centauri and its planet, Proxima B. We know this world exists. It's been confirmed through multiple independent observations using the radial velocity method, which detects the star's wobble caused by an orbiting planet's gravitational pull. Proxima B has a minimum mass of about 1.17 Earth masses, making it potentially rocky like our own planet. It orbits its star every 11.2 days at a distance of roughly 0.05 astronomical units. That's about 7.5 million kilometers, or just 5% of the Earth-Sun distance. Despite being so close to its star, Proxima B orbits within Proxima Centauri's habitable zone because Proxima is a cool red dwarf, much dimmer than our Sun. The amount of energy Proxima B receives from its star is roughly comparable to what Earth receives from the Sun. But before you get too excited, remember what we discussed earlier. Proxima Centauri is an active star that regularly unleashes powerful flares. Research published in the Astrophysical Journal Letters in 2026 examined time-resolved X-ray spectra of Proxima Centauri captured by the XMM Newton telescope. The data revealed extreme variability in high-energy radiation on short timescales. These stellar flares don't just produce light, they accelerate charged particles to high energies and strip away planetary atmospheres over geological time. Unless Proxima B has an extraordinarily strong magnetic field to deflect this radiation, or unless it's located in a fortunate orbital configuration that somehow shields it, the planet's surface is likely sterilized. Any atmosphere it once had may have been blown away millions or billions of years ago, leaving a barren, Mars-like world. But here's where things get interesting. Even if Proxima B's surface is uninhabitable, that doesn't mean it couldn't harbor life. Earth hosts extremophiles, organisms that thrive in conditions we once thought were utterly hostile to life. They live in boiling hydrothermal vents, in acidic mine drainage, in the frigid darkness beneath Antarctic ice, even inside nuclear reactors feeding on radiation. Life, as we've discovered, is remarkably tenacious and creative in finding niches to exploit. If Proxima B has subsurface oceans protected beneath kilometers of ice, similar to what we suspect exists on Jupiter's moon Europa or Saturn's moon Enceladus, those waters might be shielded from the worst of the stellar radiation. Geothermal heat from the planet's interior could provide energy for ecosystems that never see sunlight, just as deep-sea ecosystems on Earth thrive around hydrothermal vents. These hypothetical organisms wouldn't know about the stars above them or the deadly radiation bathing their planet's surface. They would exist in a dark, isolated realm, utterly unaware of the wider universe, until the day, perhaps, that a probe from Earth drills through the ice to find them. The tidal forces from Proxima Centauri could also play a crucial role. Proxima b likely experiences tidal locking, meaning the same hemisphere always faces its star, just as the same side of our moon always faces Earth. One side of the planet would be in permanent daylight, the other in permanent darkness, but this doesn't necessarily make the planet uninhabitable. Atmospheric circulation could transport heat from the day side to the night side, creating a twilight zone at the terminator, the boundary between day and night, where temperatures might be moderate enough for liquid water. Simulations of tidally locked planets suggest they could have complex climate systems, with enormous thunderstorms on the day side where heated air rises, and perpetual darkness and ice on the night side. The twilight regions could be genuinely temperate, with conditions that might support life as we know it. Or perhaps life could evolve to thrive in the extremes, photosynthetic organisms adapted to constant, intense, stellar radiation on the day side, and chemosynthetic life in the frozen darkness of the night side. Beyond Proxima b, there have been tantalizing hints of additional planets in the Proxima system. Proxima c, a candidate planet with roughly 6 Earth masses, was proposed based on radial velocity data, but its existence remains controversial. Recent astrometric studies have attempted to confirm or rule out its presence by measuring Proxima Centauri's position over time with extreme precision. As of 2026, the data remains ambiguous. Proxima c might exist, or it might be a false signal created by the star's own activity and rotation. We simply don't know yet. This uncertainty illustrates a fundamental truth about exoplanet research. Detecting planets around other stars pushes our instruments and analysis techniques to their absolute limits. We're trying to spot the gravitational influence of small rocky worlds by measuring stellar wobbles smaller than the speed a human walks. We're attempting to image planets directly despite them being billions of times dimmer than their stars and separated by angular distances smaller than a coin viewed from thousands of kilometers away. Every discovery requires heroic efforts and painstaking verification, and even then we often can't be completely certain. Imagine arriving at Alpha Centauri after a decades-long journey, only to discover that a planet you hoped to explore doesn't actually exist, that it was a data artifact, a ghost in the machine. Or imagine finding that Proxima b is indeed lifeless and barren, offering nothing more than another dead rock in a universe that suddenly seems lonelier than ever. The emotional and psychological impact on a crew who had sacrificed decades of their lives for this journey would be crushing. This is why robotic precursor missions are so critical. We need to know what's actually there before we commit human lives to the voyage. But let's assume the best-case scenario. We arrive at Alpha Centauri and find something extraordinary. Perhaps Proxima b does harbor life, even if only microbial. Perhaps there are other planets we haven't detected yet, worlds with breathable atmospheres and oceans teeming with alien biology. What then? What would be humanity's responsibility towards such a discovery? Science fiction often depicts humans colonizing alien worlds, terraforming them to suit our needs, exploiting their resources. But if those worlds already have life, even simple life, do we have the moral right to interfere? Earth's history provides cautionary tales. European colonization of the Americas brought catastrophic consequences for indigenous peoples through disease, displacement, and cultural destruction. The introduction of invasive species has devastated ecosystems worldwide. We've learned, often painfully, that intervention in complex systems we don't fully understand tends to produce unintended consequences. An alien biosphere, even a simple one, would represent a separate genesis of life, a second example of biology emerging in the universe. It might use the same DNA-based chemistry as Earth life, which would suggest that this chemical system is somehow universal or inevitable. Or it might use completely different biochemistry, different nucleic acids, different amino acids, perhaps not even based on carbon and water. Either discovery would be profoundly important for understanding life's origins and potential diversity. Contaminating such a world with Earth organisms, even accidentally, would be an irreplaceable scientific loss and arguably a moral catastrophe. The protocols for planetary protection, international agreements designed to prevent biological contamination between Earth and other worlds, would need to be far more stringent for interstellar missions than for local solar system exploration. A spacecraft arriving at Alpha Centauri would need to be sterilized to unprecedented levels far beyond what we currently achieve for Mars rovers. Even a single bacterium brought from Earth and accidentally released on Proxima B could potentially establish itself and outcompete native life, destroying an alien ecosystem before we even properly studied it. But sterilization is incredibly difficult. Microorganisms are remarkably hardy. Bacterial spores can survive extreme temperatures, radiation doses that would kill complex organisms instantly, and the vacuum of space. Studies have shown that bacteria can survive on the exterior of the International Space Station for months or even years. Some organisms enter a kind of suspended animation when conditions become unfavorable, then revive when conditions improve. Ensuring that a spacecraft is completely sterile, that not a single viable organism remains anywhere in its structure, is perhaps impossible. This creates a terrible dilemma. If we want to search for life on Proxima B, we need to land on its surface and collect samples, but the act of landing risks contamination. Do we accept this risk and proceed anyway, knowing we might inadvertently destroy what we're trying to find? Do we limit ourselves to remote sensing from orbit, which provides far less information? Or do we develop autonomous systems that can collect and analyze samples robotically, never bringing them back to Earth where they might contaminate our own biosphere, but also never allowing human scientists to examine them directly? There's another consideration that's rarely discussed: property rights and sovereignty. Who owns Alpha Centauri? The Outer Space Treaty, adopted by the United Nations in 1967, states that outer space, including celestial bodies, is not subject to national appropriation by claim of sovereignty. No nation can own the Moon, Mars, or any asteroid. By extension, this would seem to apply to other star systems as well, but the treaty was written when interstellar travel was pure fantasy. Will it hold when we're actually capable of reaching other stars? If a private company funds and launches an interstellar mission, do they have rights to whatever they find? Can they claim mineral rights on planets orbiting Alpha Centauri? Can they establish colonies and declare sovereignty independent of Earth nations? These questions sound like science fiction, but they have real legal and political implications that will need to be addressed before interstellar missions become reality. The history of maritime exploration and colonization on Earth suggests that without clear international agreements, competing claims and conflicts are almost inevitable. And what about communication with Earth during exploration of the Alpha Centauri system? Remember, there's a 4.37-year light speed delay each way. If explorers, whether human or robotic, discover something urgent, something that requires immediate decision-making from authorities on Earth, the round-trip communication time is nearly 9 years. By the time Earth receives a message and sends a response, the situation will have evolved beyond recognition. Autonomy isn't just desirable for an Alpha Centauri mission, it's absolutely necessary. Explorers will need to make binding decisions about first contact, planetary protection, resource utilization, and countless other issues without any possibility of guidance from home. This autonomy extends to ethical and moral decisions. Imagine the crew discovers not just microbial life, but something more complex, perhaps not intelligent, but sentient. Animals with nervous systems, capable of suffering. If the mission requires actions that would harm these creatures, who decides whether to proceed? The crew, who are present and can assess the situation directly. Mission control on Earth, who have broader perspective but are operating on years-old information. These aren't abstract philosophical questions. They're practical challenges that will need concrete answers before we send anyone to another star. Let's talk about what happens if an interstellar mission succeeds, if humans or their robotic proxies establish a presence at Alpha Centauri. The implications for human civilization are staggering. We would become, for the first time, a multi-star species. Humanity would exist in two separate solar systems, with communication between them delayed by years. Over time, the populations would diverge culturally, linguistically, perhaps even biologically, if the colonists adapt to different planetary conditions. History shows us that isolated populations develop distinct identities remarkably quickly. The Polynesian navigators who settled islands across the Pacific Ocean created cultures that, while sharing common roots, became quite different from each other within generations. American English diverged from British English in just a few centuries. An Alpha Centauri colony, isolated from Earth not just by distance but by years of communication delay, would inevitably develop its own culture, values, and way of life. Within a few generations, they might not consider themselves Earth humans at all, but Centaurians, a new branch of humanity shaped by a different stellar environment. This divergence could be peaceful and enriching, leading to a diversity of human cultures across multiple stars. Or it could lead to conflict, competition, and eventually perhaps even war between Earth and its offspring colonies. We like to think that humanity will have outgrown such primitive behaviors by the time we're capable of interstellar travel, but history suggests otherwise. Conflicts over resources, ideology, and power seem to be persistent features of human societies regardless of technological advancement. The prospect of human conflict spreading beyond our solar system is genuinely terrifying. Imagine warships traveling between stars, carrying weapons we can barely conceive of today. A conflict between Earth and Alpha Centauri would unfold in slow motion due to light speed delays. Fleets might be launched, battles might be fought, peace treaties might be signed, all before information about the war's beginning reached the other side. It's strategic nightmare, a game of chess where each move takes years to see and decades to respond to. But let's step back from these dark speculations and focus on something more immediate and hopeful. The actual technologies we're developing right now that could eventually enable interstellar travel. Despite all the challenges we've discussed, serious scientists and engineers are working on real projects with real funding that could, within our lifetimes, send probes to nearby stars. We've already mentioned Breakthrough Starshot, which, despite its immense challenges, represents the most concrete proposal currently on the table. The physics is sound. Use powerful ground-based lasers to push ultra-lightweight spacecraft equipped with light sails to a significant fraction of light speed. The engineering challenges are enormous, but they're not violations of known physics. They're merely incredibly difficult technical problems. Recent advances in laser technology have made the Breakthrough Starshot concept somewhat more feasible. High-power laser arrays have become more efficient and affordable. Adaptive optics systems, the technology that corrects for atmospheric distortion, have improved dramatically, originally developed for astronomical telescopes and now mature enough for large-scale deployment. The concept of a phased laser array where thousands of smaller lasers combine their beams coherently to create one immensely powerful beam has moved from theoretical to experimental. In 2024 and 2025, research teams conducted small-scale demonstrations of laser-pushed light sails in laboratory and near-Earth environments. These tests confirmed that the basic physics works. Photon pressure can indeed accelerate lightweight craft. The challenges that remain are primarily about scale. building lasers powerful enough and sails light enough to achieve relativistic velocities. These are formidable challenges, but they're engineering challenges, not fundamental physics barriers. Materials science has also made promising advances. Graphene, first isolated in 2004, has proven to be incredibly strong, roughly 200 times stronger than steel by weight, while being extraordinarily thin and light. A light sail made from graphene could potentially withstand the intense laser bombardment required for acceleration while maintaining the low mass essential for achieving high velocities. Carbon nanotube structures offer similar advantages, with exceptional strength-to-weight ratios and the potential to be woven into larger structures. Metamaterials, artificially structured materials with properties not found in nature, offer another avenue. Researchers have created metamaterials with unusual optical properties, including the ability to reflect specific wavelengths with near-perfect efficiency while remaining incredibly thin. A light sail made from carefully designed metamaterials could potentially optimize both mass and reflectivity, squeezing every bit of acceleration from each photon that strikes it. The spacecraft payload itself is also benefiting from miniaturization trends in electronics. Modern smartphones contain more computing power than the computers that guided Apollo missions to the Moon. Sensors that once required bulky equipment now fit on chips smaller than your fingernail. A spacecraft the size of a postage stamp, which is roughly what Breakthrough Starshot envisions, could potentially carry cameras, spectrometers, magnetometers, communication equipment, and enough computing power to operate autonomously. But, and this is a critical but, miniaturization creates its own challenges. Smaller components are more vulnerable to radiation damage. A cosmic ray passing through a grain-sized spacecraft has a much higher probability of hitting something critical than the same ray passing through a car-sized spacecraft. Redundancy becomes difficult when you're trying to fit everything into a package massing just a few grams. And communication from something so small is particularly challenging. The power available for transmitting signals back to Earth is limited by the spacecraft's size. A postage stamp probe can't carry large solar panels or nuclear reactors. It might harvest a few milliwatts from a tiny solar cell, or perhaps store energy in a minuscule battery charged during the laser acceleration phase. That's barely enough power to operate the electronics, let alone broadcast a signal strong enough to be detected across 4 light-years of space. The radio signal from such a tiny transmitter would be unimaginably faint by the time it reached Earth. This is where quantum communication might play a role. Quantum entanglement, the phenomenon where two particles remain mysteriously connected regardless of distance, has been proposed as a possible solution to interstellar communication challenges. If you could create entangled particles, keep some on Earth and send others with your spacecraft, you might be able to transmit information instantaneously across any distance, bypassing the light speed delay entirely. It sounds perfect, too perfect. And unfortunately, it is. Despite what some popular science articles suggest, quantum entanglement cannot be used for faster-than-light communication. This isn't a technological limitation, it's a fundamental feature of quantum mechanics. When you measure one of an entangled pair, you instantly know the state of its partner, but you can't control what state you get. The information that travels instantaneously is fundamentally random. To actually communicate specific information, you still need a classical channel, radio signals, light beams, something that travels at light speed or slower. Quantum communication does offer other advantages, particularly for security and certain types of data processing, but it won't solve the light speed delay problem for interstellar communication. Any signal from Alpha Centauri will take 4.37 years to reach us, no matter what technology we use. This is a hard limit imposed by the structure of space-time itself, and no known physics offers a workaround. Let's talk about propulsion systems beyond light sails. Nuclear pulse propulsion, the concept of detonating nuclear bombs behind a spacecraft and riding the shockwave, was seriously studied in the 1950s and 60s under Project Orion. The physics is sound. Nuclear explosions release enormous energy, and a massive shock absorber could convert that energy into thrust. Calculations suggested that an Orion-type spacecraft could potentially reach a few % of light speed, making interstellar journeys feasible within centuries rather than millennia. The challenges are obvious. First, you need to carry thousands of nuclear bombs, which adds tremendous mass. Second, the engineering required to build a shock absorber that can withstand repeated nuclear explosions at close range is daunting. Third, there are international treaties banning nuclear weapons in space, though these could theoretically be modified for peaceful scientific purposes. Fourth, launching such a craft from Earth's surface would be catastrophic. The radiation and fallout would be unacceptable. You'd need to assemble it in space and ignite it far from Earth. But perhaps the most fundamental problem with nuclear pulse propulsion is the rocket equation again. You're carrying your fuel, the bombs, with you, so you're accelerating an ever-diminishing mass. The efficiency gains aren't as good as they first appear. Still, for initial interstellar missions where you're not trying to achieve extreme velocities, nuclear pulse propulsion might be viable. A mission to Alpha Centauri using this method might take 500 to 1,000 years, which is still faster than anything we've achieved with conventional rockets. Fusion propulsion offers better theoretical performance. Instead of splitting heavy atoms like uranium or plutonium, fission, fusion combines light atoms like hydrogen into helium, releasing energy in the process. This is the same process that powers the sun and hydrogen bombs. Fusion releases more energy per unit mass than fission, and the fuel, hydrogen isotopes, can be much lighter and more compact. A fusion rocket could potentially achieve higher exhaust velocities, making it more efficient for interstellar missions. The problem is that we still haven't achieved sustained, controlled fusion on Earth. Experimental fusion reactors like ITER, the International Thermonuclear Experimental Reactor currently under construction in France, and NIF, the National Ignition Facility in the United States, have made significant progress. In December 2022, NIF achieved fusion ignition, producing more energy from fusion than was delivered to the fuel pellet for the first time in history. This was a genuine breakthrough, proof that controlled fusion energy is possible. But there's always a but. Achieving net energy gain in a laboratory is vastly different from building a practical fusion rocket. The NEF experiment required enormous lasers and complex equipment filling a building the size of a sports stadium. Making fusion reactors small enough, light enough, and efficient enough to power spacecraft is an engineering challenge that may take decades to solve. And even when we do develop functioning fusion rockets, they'll still face limitations from the rocket equation. They'll be better than chemical rockets, possibly even better than fission rockets, but they won't be magic. Antimatter represents the theoretical pinnacle of chemical energy storage. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation E each mc2 ET@c2. This is the most efficient energy release possible under known physics. For comparison, fusion converts less than 1% of mass into energy, and chemical rockets convert essentially zero. They just rearrange molecular bonds. If you could build an antimatter rocket, the exhaust velocity would approach the speed of light itself. The rocket equation would finally work in your favor. Relatively modest amounts of fuel could accelerate a spacecraft to significant fractions of light speed. An antimatter-powered mission to Alpha Centauri could potentially make the journey in decades rather than centuries or millennia. It sounds like the perfect solution. Except that antimatter is absurdly difficult to produce and even more difficult to store. Currently, facilities like CERN's antiproton decelerator produce tiny quantities of antimatter, a few nanograms per year, at enormous cost. Estimates suggest that producing 1 gram of antimatter using current technology would cost roughly $62 trillion and require more energy than the entire world produces in a year. We're not talking about scaling up existing technology. We're talking about revolutionary breakthroughs in antimatter production efficiency. And even if we solve the production problem, storage is nearly impossible. Antimatter cannot touch normal matter. That's the entire point. The moment an antiproton touches a normal proton, they annihilate in a burst of gamma rays. You need to store antimatter in magnetic bottles or traps that suspend it in vacuum, never allowing it to touch the container walls. The most advanced antimatter traps can hold a few 100,000 antiprotons for several days before losses become unacceptable. Scaling this to grams or kilograms of antimatter stored reliably for decades during an interstellar journey is so far beyond our current capabilities that it's essentially science fiction. There's also the problem of extracting useful thrust from matter-antimatter annihilation. The energy is released as gamma rays and other high-energy particles traveling in all directions. You need to somehow channel this into directional thrust, which requires materials that can withstand the most intense radiation environment imaginable. Proposals exist: magnetic nozzles that could direct charged annihilation products, solid or liquid reaction masses that absorb gamma rays and get expelled as heated plasma, but these remain entirely theoretical. So while antimatter propulsion represents a beautiful theoretical solution, the practical challenges place it firmly in the maybe someday, but not anytime soon category. It's not impossible, it doesn't violate physics, but the engineering gap between theory and practice is enormous. This brings us to the most exotic concepts, the ones that push against or even seem to violate known physics, warp drives and wormholes. These concepts come from general relativity, Einstein's theory of gravity, and space-time. According to general relativity, space-time itself is flexible. It can be curved, bent, stretched, and compressed by mass and energy. This isn't metaphorical. Space-time is a real physical thing with geometric properties that affect how objects move and how light travels. Black holes are extreme examples of space-time curvature. Their gravity is so intense that space-time becomes so severely curved that not even light can escape. But the equations of general relativity allow for other exotic space-time geometries. In 1994, physicist Miguel Alcubierre published a paper describing a theoretical space-time geometry that would allow faster-than-light travel without violating relativity. The concept, now called the Alcubierre drive or warp drive, involves contracting space-time in front of a spacecraft while expanding it behind, creating a bubble of normal space-time that carries the ship along. Inside the bubble, the spacecraft wouldn't be moving at all relative to local space-time. You'd experience no acceleration, no time dilation, none of the relativistic effects we discussed earlier. But the bubble itself would move through space, potentially at speeds faster than light. From an external perspective, you'd appear to travel vast distances almost instantaneously. A trip to Alpha Centauri could take days or weeks instead of decades. It sounds miraculous and deeply suspicious. How can you travel faster than light without violating relativity? The answer is that you're not traveling through space faster than light. You're moving space itself. Relativity forbids objects from moving through space-time faster than light, but it places no limits on how fast space-time itself can move or change. During cosmic inflation, a brief period shortly after the Big Bang, space expanded faster than light, carrying distant regions of the universe beyond our observable horizon. The Alcubierre drive would exploit the same principle on a local scale. But here's the devastating problem. Creating the Alcubierre space-time geometry requires exotic matter with negative energy density. Not just negative mass, but negative energy, a property that we've never observed in nature and that may be impossible. Quantum field theory predicts that certain vacuum states might have negative energy density under very specific conditions. The Casimir effect demonstrates something vaguely similar. But the quantities are microscopic and the conditions are highly constrained. To create an Alcubierre bubble large enough to contain a spacecraft, you'd need exotic matter with total negative energy equivalent to the mass energy of Jupiter, or perhaps even a star, depending on the specific configuration. We have no idea how to create or manipulate such matter, no idea if it even can exist in macroscopic quantities, and no idea how to shape it into the precise geometric configuration required. Some theoretical analyses suggest that Alcubierre drives might be fundamentally impossible due to quantum effects that prevent the formation of the required spacetime geometry. More recent work has explored modified versions of the Alcubierre drive that might require less exotic matter or might use different spacetime geometries. In 2021, physicist Eric Lentz proposed a theoretical warp drive configuration using conventional positive energy, though it would require staggering amounts, roughly the mass energy of Jupiter concentrated into a small volume. This still seems impossibly difficult, but at least it doesn't require hypothetical exotic matter that might not exist. The bottom line is that warp drives remain firmly in the realm of speculative theoretical physics. They're not proven impossible, but we have no practical path toward building one with any foreseeable technology. They're conversation pieces for theoretical physicists, not engineering projects. Wormholes, shortcuts through space-time connecting distant regions, face similar obstacles. The Einstein field equations allow for wormhole solutions, but stable, traversable wormholes require exotic matter to hold them open against their natural tendency to collapse. And even if you could create a wormhole, you couldn't use it to travel to Alpha Centauri unless you first transported one end of the wormhole there by conventional means, which defeats the purpose. So where does this leave us? We've explored the challenges of interstellar travel from every angle, the vast distances, the energy requirements, the deadly radiation, the engineering obstacles, the biological challenges, the exotic propulsion systems that remain beyond our grasp. The picture seems bleak. Alpha Centauri is tantalizingly close by cosmic standards, yet almost impossibly far by the standards of human technology and lifespans. But here's what I find fascinating. Despite all these challenges, serious research continues. Breakthrough Starshot has funding and talented scientists working on real experiments. Fusion energy is progressing from perpetual future promise to actual demonstrable achievement. Materials science keeps delivering stronger, lighter materials that would have seemed impossible decades ago. Miniaturization continues to pack more capability into smaller packages. The journey to Alpha Centauri isn't something we'll accomplish next decade, or probably even next century. But it's not forever beyond reach either. It's a grand challenge that will require patience, persistence, incremental progress, and probably breakthroughs we can't yet anticipate. Every generation of humans has faced challenges that seemed impossible with their current technology. Many of those challenges were eventually overcome. In 1903, the Wright brothers achieved the first powered flight, covering 37 meters in 12 seconds. People who witnessed that flight were still alive when Neil Armstrong walked on the moon in 1969, a journey of 384,000 kilometers accomplished in a single human lifetime. The progress from Kitty Hawk to the moon seemed impossible in 1903, yet it happened within 66 years. Perhaps the journey from our first tentative steps to the moon to the first probe arriving at Alpha Centauri will take not 66 years but 660 or even 6,600. The timescales are longer because the challenges are immensely greater, but that doesn't mean it won't happen. It means it will require long-term thinking, multi-generational commitment, and a willingness to work toward goals we personally will never see accomplished. This is perhaps the deepest challenge of interstellar travel, not the physics or engineering, but the psychology and sociology. Our species evolved to think in time frames of days, seasons, and individual lifetimes. Building pyramids or cathedrals that took generations to complete represented the outer limits of our long-term planning. Interstellar travel demands thinking across centuries or millennia, committing resources to projects whose benefits will accrue to distant descendants we'll never meet. Can we do that? Can humanity organize itself to pursue goals on such timescales? History provides mixed evidence. We've successfully undertaken some long-term projects: the Great Wall of China, the gradual accumulation of scientific knowledge across centuries, the preservation of cultural traditions across millennia. But we've also demonstrated shocking short-sightedness, destroying environments for short-term gain, failing to address climate change despite knowing the consequences, allowing political conflicts to derail beneficial international cooperation. If you made this far, make sure to give this video a like. The universe is full of paradoxes and mind-bending concepts. Speaking of which, if you're curious about another cosmic mystery, check out my video on the screen. Why is space so cold when everything in it is burning? You'll discover why the vacuum of space is freezing despite being filled with blazing stars, and the answer might surprise you. See you there.